Hello there. We're going to be progressing with our course by looking at real life applications, starting with mechanical modeling. So sit down, and after mechanical, we're going to look at electrical. I think that's what you've been long waiting for as electrical engineering students. Without further waste of time, let's progress with the work. Nothing changed as far as my contacts are concerned. I'm still waiting for UJ, obviously. 5161 is my office number. And 08453533108 is my cell number. As I promised, we're going to look at mechanical systems. The objective of the chapter being to make you understand the modeling of forces that act on mass or spring, modular damping with relation to forces as well. Damping is more artificial friction. It's used in building to reduce the movement caused by earthquakes, used in cars to reduce drastic motion when the cars hit things like speed humps and so forth. Like a shock, more of like a shock absorber. And we're gonna have equations to represent that are aligned to Laplace transfers. In this section, we look at the single force which is applied to a spring in the form of pulling, where the displacement increases with respect to time, or in a form of pushing, where the displacement is reduced with respect to time. But the spring won't just allow the force to act on it. It will have some form of coefficient of resistivity expressed in Newton meters. Overall, the force of a spring with respect to time multiplied by the proportional constant, or is rather equals to the proportional constant multiplied by the displacement with respect to time. So if we have to change the domain from T to the P, this is what we have. Wherever there's T, you placed P, making the equation f of P equals to K x into P, xp, Windows XP version. We take a reciprocal of this. We multiply both sides by x of P. We're gonna get that, which now means the input, which is the force, being transferred by this to make the displacement. So that's how we translate the input force of a spring to become a displacement of a spring. There is that relation. Now, we've got a thing called a viscous damper used to prevent or to protect buildings against damages resulting from movement when or earthquake occurs, more like a shock absorber. You can have a repulsion force or displace, which causes FD for damper, displacement x of t, and we can have a contracting force which oppose or tend to reduce the displacement. Remember, there is a velocity which is already occurring. So that force acts on a velocity, making the width a form of resistivity, which is damping coefficient. Now, to get velocity, we differentiate, or the rate of change in displacement, we differentiate displacement with respect to time, and then multiplying that to the damping coefficient will result to the displacement, or rather damping force. So if we again make it to P domain, we put P and we replace that by P, coming from symbols used in Laplace transform. In this case, the first derivative, it's like assigned to, or replaced by letter P, showing that we took a derivative of a displacement which used to be there with respect to time. So time domain to P domain, that's a constant, not change. The derivative, we show it by P. So we have that. And if we follow the previous method, we take the reciprocal of this, we multiply by 1 over xp. And this will be the multiplying factor of the force, which is in this case, damping force, F of D, and then we'll transfer it to become a displacement. Closer look at the equation, we will find that displacement force, we just make it force P, D, and then it becomes P. So the significance of this thing here is like, it won't even really matter now when we use P. Which force was it? It was the damping force, it was the displacement force, and so forth. So the constant damping coefficient can be calculated in this fashion. We move along, forces on the mass. This in grade 12, we've done a lot of them. Where is, if a force is applied on a mass, Fm, then its acceleration, the way it accelerates the mass, it will be proportional to that particular force. So, but acceleration itself, yeah, is a derivative of this velocity. Now, which velocity is a derivative of a displacement? Now you've got a second order derivative of displacement to get to acceleration. So that's what we have there. Second order derivative of displacement multiplied by f. That's acceleration. And now we transfer this to P domain, T, P, then MP, Pumalanga there. For second order, note 2 there, where P is raised to. Second derivative of a displacement over P domain. Now we take a reciprocal and multiply by xp, and xp into P of f into divided by f into P is 1 over mp squared. So now that's your gain. When you apply force to a mass, Fm, to that, through that gain, it will translate onto a displacement. Now, closer look of this now, MA, A being the first derivative of velocity, which makes it the second derivative of displacement. And now we change to P domain, where we see M follows off and then it becomes F of P, T replaced by P, M there, derivative second, we show P raised to 2, X of P. Then from there, we can work out, come up with the equation for mass in terms of force and P derivative of X of P. So let's just look at the equation which is going to put everything onto perspective. We have a force which creates displacement, but we've got a spring which opposes the force, doesn't allow it, and we've got another spring which opposes the force. So these forces work together, we can add them. And now we've got D1, which is a coefficient of friction, which acts as a damper in this instance. Now on the representation, we've got the force of a mass, which is not shown there. And then we've got that one of a damper, first derivative, and then we have K2, K1, which is going to be added, and the force and X, and then the force act on a mass. So force acting on a mass, we know we have to get second order derivative of displacement, and then for damping, first derivative of displacement. And now this is just a product of K and X, which is already shown there. Kx of t, K2x of t, then you factorize the, take xp out, you got that. Take the reciprocal and multiply by, always multiply by that, then that you have the x of p, which is a displacement, which is the primary thing. We're looking at displacement. How do you transfer? So you can have your own little transfer function there, where you're gonna have, now I don't know how you're gonna call your force because many forces. So combined force, which will be transferred to a certain displacement. Combined force, which will be transferred to a displacement x. Okay, so we've got this, by the way, is called a free body diagram. It's not like an actual diagram which you had there. So with that, folks, we come to the end of your lesson. We'll be sending you further problems for rehearsal. But then that will be in terms related to these things which we covered, spring, masses, and so forth. And guys, thanks for attending, and good luck. Don't forget to practice.